Okay, this is section 3.9. The topic is called differentials, and this video will be in a couple of different parts. Here's the first part. Okay, remember that the derivative value always represents slope values on a given function, and generally when we talk about slope, we talk about between 2 points, we talk about, say, a rise over a run. So that slope can be computed as the difference in the y values over the difference in the x values. Remember that? y2 minus y1 over x2 minus x1. Now that is sometimes written delta y over delta x, where delta y means the change in the y value and delta x means the change in the x value. And that would be the slope of a line between 2 points. When we write derivative, we don't write delta y and delta x, we write dy and dx. And remember that was derived by taking those 2 points, moving them closer together so that eventually we had simply 1 point. And the slope of that line was called dy dx. So these quantities, dy and dx, you can think of them like a delta y and a delta x. They're small quantities, and they're called the differentials. They represent small, non-zero values for the changes in y and x. Specifically, if y is equal to f of x, then we write that dy dx, the derivative, is equal to f prime of x. Now, just take that equation and multiply both sides by dx, and you have this relationship. dy is equal to f prime of x dx. This is called the differential form for the derivative. It's really the same as the derivative. I've just separated the quantities dy and dx because they really just represent small quantities. Differentials are used to approximate changes in output values, that's y values of a function, given small changes in the input values, that's the x values. Let me draw a picture to show you what I mean. So if I have some function moving along, I'll just create a function there. And I am looking between one point to another point. Then to move from one point to another point, I could find the slope of that secant line. Okay, the slope of that secant line would be the change in the y value over the change in the x value. That would be delta y, that would be delta x. If instead I were to create a tangent line right here at this initial point, okay, the slope of the tangent line would be dy dx. Now if I make my dx value the same as my delta x value, so there's my dx value, then this amount right here that I'm marking in blue, that is the dy value, because the slope of this line is dy over dx. What you can see from here is that the dy value is an approximation to the delta y value. It's not exactly the same. In this case, it's a little smaller. But as long as the dx is a small enough value, the delta y and the dy will be close to the same amount. The delta y is the actual change in the y value on the function f of x. Dy is the change in the y value on the tangent line. And the key is, if my change in x is small enough, then this tangent line is pretty close to being the same as the function, and so my dy is a good approximation of my delta y. Okay, so that's what we're going to be using it for, is an approximation to our delta y. Okay, first let's just practice how you find this thing called dy. So I'm going to take the derivative of this equation. So dy dx equals 12x squared plus 7. Now I'm just going to treat that dx as a quantity, so I can multiply both sides by it. dy is equal to 12x squared plus 7 dx. Again, that's called differential form. dy is the differential of y. Okay, do the same thing on part B. So pause the video, find the dy expression just like I did for A, but find that for B, and then when you're ready, start the video back up. Okay, so I assume you started the video back up, so here we go. Y could be written as 5 minus x squared to the 1/2. So dy dx, the derivative, is 1/2 5 minus x squared to the -1/2 times negative 2x. That was the chain rule I applied. So dy dx is equal to, I'll reduce the 2 and the negative 2, and I'll get a negative x, and I'm going to go over the square root of 5 minus x squared, because that's a negative 1/2 power. Then all I do to write the differential form is I solve for dy. So dy is negative x over the square root of 5 minus x squared times dx. Again, that's just called differential form. Okay, now what do we use these differentials for? Let me give you an example that will kind of show you one way that we might use these. Okay, consider the function y equals the square root of x. So the first thing I'm going to do is I'm going to get a picture of y equals the square root of x. I know that that graph starts at 0, 0. I know it goes through 1, 1. I know it goes through 4, 2. Okay, so I know it does something like that. There's the graph of y equals radical x. Okay, it says find the value of dy given that x is 1 and dx is 0.1. So first I'm going to find the differential expression for y. So dy dx is equal to 1/2 x to the negative 1/2, which means dy is 1/2 x to the negative 1/2 dx. Now to find dy, I'm just going to substitute in the values that I'm given here, that x is 1 and dx is 0.1. Okay, so dy is equal to 1/2 of 1 to the negative 1/2 times 0.1. So if I work that out, 1 to any power is 1, and 1/2 times 0.1 is 0.05. Now, let me show you what it was that we actually just now found, this dy of 0.05. If I go to this graph that I drew here, and I go to x equals 1, if I were to go over just slightly, how much over? 0.1 over, that's going to be my delta x. So there's at 1.1. And I want to know what's the actual difference in the y values between those 2 points. So that little value right there would be the delta y. Well, this dy is not exactly it, but it's a good approximator. What the dy is if I had sketched a tangent line right at 1, the dy is the difference in the y value for the tangent line. So right there, that's my dy. So in this case, I can actually see, because this function is concave down, that my dy value is slightly greater than my delta y value. Okay? So again, that's the difference in the y values between x equals 1 and x equals 1.1. Okay, letter B, let's try a similar one. Find dy given that x is 9 and dx is negative 0.2. So again, I already know dy is 1/2 x to the negative 1/2 dx. So then that means dy is 1/2 of 9 to the negative 1/2 times negative 0.2. Okay, I'm going to work that out without a calculator. What the heck? So that's 1/2. 9 to the negative 1/2 is 1 over the square root of 9, which is 3. Negative 0.2 is actually negative 2/10. So if I work that out, I believe I get negative 1 over 30. Now, it says to use that value to approximate the value of the square root of 8.8. Okay, let me show you that picture again up there. But let me actually kind of zoom in closer, maybe around x equaling 9. So again, I have this curve here. And let's suppose I'm way out here at x equals 9. Okay, what differentials do, again, to make sure you understand, is they use a tangent line to approximate a change in y. I want to approximate the value of the square root of 8.8. 8.8 would be about here on the function. There's 8.8. So what's the difference between 9 and 8.8? Well, that difference, that dx, is the negative 0.2 that I talked about right there. So the dx is negative 0.2, but the x where I would have drawn my tangent line is 9. Okay, by computing that dy is negative 1/30, I'm saying that if I move from 9 to 8.8 on the curve, then the change in the y value is about negative 1/30. Okay, if x were 9, what would be the y value? Remember, we're on the function y equals the square root of x. So if x were 9, y would be the square root of 9, which is 3. But instead, we're finding it for the square root of 8.8, which is a difference for x of negative 0.2. So that means the square root of 8.8 would have been 3, but the difference in y is negative 1/30. So that means the square root of 8.8 is about 2 and 29/30. Now, I invite you to take just a moment to check that on your calculator. Do the square root of 8.8 and also get a decimal approximation for 2 and 29/30 and compare. And you'll see that that's actually a pretty good approximation for the square root of 8.8, which would otherwise be relatively difficult for us to approximate. Okay, I'm going to pause this or stop this recording and we'll go on to part 2.